Hey, it's Mr. R from Calculus 3, and I'm doing planetary motion from an old textbook. I posted the text, but here's the problem. It says, since the orbit of Skylab 4 has a semi-major axis of 6808 kilometers, Kepler's third law with m equal to the Earth's mass should give a period. Calculate it. So the formula that we're looking for here that's going to relate the orbital time with the semi-major axis is this third law, t squared over a cubed equals 4 pi squared over gm. M being the Earth's mass, which it says we can look up in a table. And just to kind of make sure you understand, that table was in the notes as far as what I posted, Earth's mass here. Pretty large numbers, pretty big. The other things here, G is the gravitational constant, also given in the notes. So we have that. You can look that up. But let's see here. So just plugging everything we have in, the A, but the A is in kilometers, and one thing we need to notice is that I changed it to meters because the gravitational constant is in meters cubed. So if I put all that in, I've got quite a mess with some units and some scientific notation, but if I'm very careful, push through, and I get 5590 seconds to take Skylab around Earth, or 93 minutes. Okay, let's take some of those highlights off just so they're easier to look at if you pause it a little bit later. So the hard thing here is following the scientific notation. Okay, here's a second problem. It does pretty much the same stuff. It's about Viking 1. The Viking 1 orbiter, which surveyed Mars, so in this case it's going to go around Mars, so that's important to know. So when you do that, you have to look at the mass of Mars, which is different than the mass of Earth. So we're using the same formula, but maybe with different numbers. We'll still be using the same universal gravitational constant. But it says it has a period of 1,639 minutes. One thing here is that the gravitational constant has seconds in its units, so we're going to change the 1639 minutes to seconds. And they gave us the mass, and it says find the semi-major axis. So we're using the same formula that we used before. We just solved for a cubed. We follow through with all the units. Eventually we get down to something in meters. Which is 21,891 meters, or 21,891 kilometers. So just kind of push through the scientific notation there. If you have problems, let me know. I'm going to erase all these marks. And the reason we did 4 is because 5 says to use 4. So let's see if I can get this pulled over. And 5 is a very easy problem. But 5 says the Viking 1 orbiter was 1499 kilometers from the surface of Mars at its closest point. So I drew a little diagram here. And what we know is the orbit of a satellite around any planet or sun is an ellipse. And in this case, the closest it ever got to Mars was 1499 kilometers. That's the closest. Another name for that is the perigee. And it says it was 35,800 kilometers from the surface of Mars at its furthest point. So since it's an ellipse, Mars is at one of the foci of the ellipse, so it's not in the in the middle. So at the furthest point, that's also called the apogee. So we put Mars right in the middle. It says use this information together with the value obtained in exercise 4, which is the previous problem, to estimate the average diameter of Mars. So we figured out in the previous one that the semi-major axis was about 22,000 kilometers, And basically what the semi-major axis means is it's the halfway point from the longest longest diameter across this ellipse, so about the halfway point in there. So the left side of that red mark would be about 22,000 kilometers. The right side of that would be about 22,000. So basically, we've got these two things, two measurements on either side of Mars, and then Mars in the middle. Well, we can take the 22,000 kilometers, and that's about 44,000 kilometers over here. And then we can take the furthest point, the nearest point, which is about 37,000 kilometers, and we can make up the difference, which would be the diameter of Mars here, which is about 6,500 kilometers. So think about that for a little bit. We have the left side of Mars, the right side of Mars, but Mars is trapped in the middle, and what we just calculated in problem 4 was the total, well, half the distance all the way across, which we can double. Okay, let's get these marks off in case you want to look at them later. You can blow up the video. Boop, boop, boop. All right, thank you.